So welcome everyone to the third Machine Learning at Helmholtz-Zentrum Gestacht online only seminar. We'll have a few announcements and get to our topic for the week. First of all, we have a website for our seminar series. I'm going to quickly show this in the screen share. In addition to our mailing list, you can see our past topics, our past videos. We're going to drop links to all the papers and resources we discuss in there. It's at m-dml.org/seminar. Next, we are still looking for people to do 5-minute presentations. Today we have Linda van Garderen presenting her work. If you want to do this in some subsequent week, just please let us know. We'd also be interested in people presenting their work more in depth or presenting a paper they're interested in going over in depth and basically taking over the machine learning seminar for some piece of research, some piece of software, something for 1 week. And finally, our last announcement is that, so this has been a really great success, I think, the first 3 weeks. It's a lot of work to put together, and it's also a lot of work for people to read one of these papers every week in addition to all their own work, all their own reading. So we're thinking strongly of making this every 2 weeks instead of every week, but we're open to everyone's input, and we'd like to hear what you think. So Linda, I will turn this over to you for 5 minutes. I'm going to turn off my screen share, and you can take over.
Great. Let me start sharing then. The moving of the air in the high atmosphere as happened, but leave the thermodynamics free. We do this by simulating the extreme event under study in a world as we know it, and then a world without climate change. We call this the factual world and the counterfactual world. And we create that using the global atmospheric model ECOM6. Some of you may have heard of it. And that's a so-called high resolution, 60 kilometers at the equator. This is the highest resolution available in ECOM. This will not be made any higher, as now they're working on ICON and no longer on ECOM6. The sea surface temperature, sea ice concentration, and greenhouse gases are prescribed through NZEP data. That is the SST and SICR NZEP reanalysis data. And to make sure we don't, that we can simulate the past event as was and not just a random climatological state of the atmosphere, we use spectral nudging. Now, I can go on for a very long time on exactly how the spectral nudging is applied, what it does, how it works. But as I only have a few minutes, I will just tell you that I spectrally nudge to make sure we can do a representation of a historical event. We do that in the world as we know it, and then we create a world that could have been a counterfactual world. And the difference between these two worlds or these two simulations is that the sea surface temperature and the sea ice concentration are taken, but without the warming pattern of the last century. so that we have the sea surface temperature and sea ice concentration that could have been in a modern world if it wasn't for climate change. And we put the greenhouse gases back to pre-industrial values. These 3 points are the only differences between the counterfactual and the factual world. This is how they are different from each other. And I would like to show you some results from 2 heat waves that I studied. The first on the top, this is the European heat wave. And I want to show you that here, this is the temperature in Celsius. This is the 1st of June all the way to the 1st of September for this domain. So this is a domain average. The green is climatology 5 to 95 percentile. And then the results for the factual world in blue and the counterfactual in red. We have 3 members for each. And you can see there was a heat wave here in June, and then there's a heat wave here in end of July, August. So there was a dip, but in general, this is the whole heat wave. It's clearly visible the factual world is warmer than the counterfactual world for all members. And that the heat wave here rise above the 95th percentile, which is pretty high. So here we have the Russian heat wave. We do the exact same thing, 1st of June till the 1st of September. But then for 2010. And the 5th to the 95th percentile, here again, we have the factual in blue and the counterfactual in red. Here's the heat wave that was very extreme. It was the most extreme heat wave on record for Europe. And again, we see that the factual is above the counterfactual for all members. We see that the thermodynamics alone, so they have both have the same dynamical situation in the higher atmosphere. So the circulation is the same, but the thermodynamics have differences due to climate change. And we can also show this in the domain. Here we have the European domain, 2003, and we averaged the first week of July, second week of July, and then half August, second half of August. This is what actually happened, the temperature in colors and the geopotential height at 500, set 500 in lines. So here you see that here is where the heat wave was the most extreme. What you see here is very interesting. This is the key result, basically. I took the average of the 3 factual members minus the counterfactual members. This is the temperature at 2-meter height, which means if it is above 0, the factual world is warmer than the counterfactual world, and in blue the opposite. The stippling means that the 3 members of the factual world were all higher than the 3 members of the counterfactual world, so that we have a stable sign. As you can see here, this is all over the land mass, basically. There are some exceptions. There are mountains here. There's some exceptions, but we see a clear sign that the factual world is warmer than the counterfactual world, with some up to about 2.5 degrees, which is quite a lot, 2.5 degrees. And for the Russian heat wave, we have the same thing here. This is the temperature of the factual world with the geopotential height at set 500. And here we have the factual minus the counterfactual members, 2-meter temperature. And we see very strongly that during the heat wave, during this blocking situation, we have much, much higher differences between the factual and the counterfactual world, between the climate and the climate change and climate change free world. And also the stippling is much more dominant in during the heat wave, which means that the members are really the members of the factual and the members of the counterfactual are really split. All of them, they're not overlapping in any way. As soon as the heat wave is over, the sign becomes much less. It's still there, but it's much less strong. So this is now a part of the results for my first paper that I wish to submit before Easter, maybe next week if necessary, doing some final corrections. This is part of my first paper on explaining the method, how it works, put a lot of attention on spectral nudging and on the case-based storyline method. But in the future, I will also look at other extremes, such as extratropical storms, typhoons, and large-scale rain extremes. I already looked a bit into typhoons. That may not be the modeling and the setup may not be the most beneficial for that. But for extratropical storms, it would be very nice to look at that. So this is in very short what I do.
Thanks a lot, Linda. That was really interesting. I've got just one quick follow-up question. So you have a counterfactual scenario which is cooler than the factual scenario. Have you looked at the opposite direction and asked, what if the counterfactual were hotter? What would the extremes look like then?
Yeah, so with storylines, you can choose all different kinds. So I only have one storyline, the pre-industrial situation, basically. But you can also take it to the future. So what if my world has higher SSTs, or you can create any situation and run the models for that. For this moment, I have the storyline of the present world and the storyline of the world that could have been without climate change. That's what I have at this moment. That's how I have developed the method and can apply it in ECOM at this moment. But it can be used in any way, really. You can use it for future scenarios, anything.
Well, great. Thank you very much.
You're welcome.
All right, so I will take back over the screen sharing and we will move on to the main paper we're discussing, which is this MetNet paper by Google Research and Google Brain. So, okay, what are they trying to do? What data are they using, and how do they go about this? So the problem here is one of weather prediction. Specifically, they want to predict the precipitation rate. So here on the screen, you should see in the lower image, this is the precipitation rate estimated using the multi-radar, multi-sensor system of ground-based radars across the continental United States. And they're trying to predict it in the future, given the current and past precipitation rates, as well as 16 different hyperspectral imaging channels collected by satellites, like in the image that you can see at the top. So the inputs are the past precipitation rates and the current precipitation rates. The outputs are precipitation rates in the future up to 8 hours ahead. The other inputs are the 16 channels of GOES, Geostationary Operational Environment Satellite, which has also been published online as a benchmark data set, which is linked in the main paper we'll cover. All the inputs and all the outputs are gridded at about 1 degree of latitude and longitude, which I believe comes to about 1 kilometer square. And the data is available every 2 minutes, although this paper that we're covering uses it in 15-minute increments. Okay, so there's a really nice blog post to go along with this paper, which I highly recommend. They show what the data looks like. So here's the output of their network, the probability of precipitation at above 1 millimeter per hour in the future, and you can see here is the prediction time right in minutes. So we're going up to 8 hours, 480 minutes. And then they're comparing this to a single ensemble member from a deterministic weather prediction. This here is actually just the ground truth. So this is actually where in the future you have the rainfall over 1 millimeter per hour. So we'll cover their model, we'll cover how it works, and we'll figure out how they put together all these different components. So what they compare to, generally their benchmark, let me switch to the main paper here. They're compared to deterministic numerical weather prediction using a physics-based simulator. In particular, they're comparing to this high-resolution rapid refresh system from the National Oceanic and Atmospheric Association. So what we'll have when we look at these comparisons is, in ground truth, we have at different times in the future the precipitation patterns. We have the probabilistic outputs, and we'll get exactly what that means in a little while, of MetNet, this neural network built by Google. And then we have a single deterministic prediction by a physics-based simulator on the right, HRRR. Okay, so one of the first things they point out, and this is a key challenge of this sort of prediction, and it also touches in some ways on the previous two papers we've done, is the idea of incorporating context. We can see this here in in the blog posts here, right? If we want to predict the weather at some point in the future, we need to condition that output, that prediction, on a large region of the input, right? We need to, in their case, they want to predict in a 64-kilometer region at the center of this square, and they want to condition it on this very large 1024 by 1024 kilometer region. And so one of the reasons you need to do that is simply the clouds might move over 8 hours. Also, you have other processes like convection, but all of this transfer information. So the farther in the future you want to make a prediction, the more of the current state or the past state you have to take into account. And this is a technically challenging thing to do with a neural network. When you're talking about 1024 times 1024, that's 1,000,000 dimensional inputs. It's very difficult to get a neural network to learn that in a stable way. You need some kind of tool. We talked about convolutional approaches last week, in particular convolutions on spheres. There are other approaches we'll cover today, in particular recurrent networks and self-attention. But all of these are different ways of getting at that problem, that if you were to just map all the inputs onto all the outputs, you would have so many parameters and so much data flowing around, you would never fit the thing in memory. You'd have too many parameters and you'd overfit, and you'd run into all sorts of similar issues. But so how do you know how much of a context? How big should this outer square be? So in the paper, they make this pretty simple argument. They say, well, if information, say a cloud or a wind, can move at about 1 kilometer per minute, that is to say 60 kilometers an hour or 26 meters per second, then if we want to compute 8 hours in the future, then we need something like 480 kilometers on either side of the place we're predicting. So if they want to predict in a 64 by 64 kilometers square, they need to extend this to 1,024 kilometers total for the inputs. Okay, so this is the problem that they're trying to solve. They're trying to predict these weather patterns based on 16 of these inputs, based on the current and past states of the precipitation rate in millimeters per hour, and based on some other features they'll feed into the neural network, such as the latitude, longitude, time of day, season of the year, and so on. And the ingredients they use to build this network, I'm going to jump to their figure 2, using quite a few. They're using convolutional networks, which we've covered before. They're using a recurrent network, in which takes as inputs the state of the system at multiple times and aggregates them all into one output in an efficient way. They're also using self-attention, which we'll cover. This is a very new and very powerful and very successful trend in machine learning. There's attention networks. It brings a lot of new capabilities. It's beating a lot of challenges, like getting the first place in a lot of different areas. And it also includes some limitations, and we'll discuss those too. And then another interesting ingredient of this method, as we mentioned, is it outputs probabilistic estimates, not just the locations of rain, not just the amount of rain, but the probability of different levels of rain at each point in space. And we'll talk about how they do that too. So the first part, the convolutions in space and the recurrence in time, I'm going to turn over to Marcel, who's going to cover the convolutional LSTM paper briefly that they build on. So Marcel, I'm going to turn off my screen sharing and turn over to you now.
Hello, everybody. Can you hear me and can you see my screen?
Yes.
Okay, great. Then I'm gonna quickly get lost in the paper. Yeah, here is where we were. So David talked about the inputs. So we have a bunch of satellite images and radar images, And as he mentioned, we have these different channels for elevation, longitude, latitude, and day and time. And then we have a spatial downsampler, which you can think of as just a feed-forward convolutional network right now. And then we have, for different time points at different delays, we have these stacks of inputs and their nonlinear computations that the spatial downsampler has produced as a representation internally. But we have a bunch of them. So here you see these dot, dot, dots, a sequence of these tensors. And what we need to do is we need to somehow summarize all of them together into a single tensor that we can then pass on to the spatial aggregator part of the network that David will then later talk about. And the way this is done is through a temporal encoder that is a convolutional LSTM, as it's called here. To understand what this thing does is we'll be looking into this paper, which introduced the convolutional LSTM. Also in the context of weather forecasting, actually. And to quickly understand what this thing is meant to do, what it does is it for every time point, it computes a sequence of internal states that each depend on the previous one, and do computations on the sequence. It operates as an LSTM, which I will introduce with this blog post a bit. So this is a classical blog post from Christopher Olah on understanding LSTM networks. For anybody interested, here is the link. So a non-convolutional LSTM, these things have been around for a long time, more than 20 years, is a network that operates on sequences of data. So you have an input sequence that you feed in one element at a time into the network. And the network is recurrent in the sense that its own state is combined with the current input to produce the new states. So the inputs classically are vectors, and then the state variables themselves are vectors as well. The problem with these recurrent neural networks is that if you have short dependencies for hidden states onto the inputs, this usually works quite decent. If you have very long distances between the information and where it comes in the inputs and where you actually need it further down in the sequence, then these networks do usually not work as well. And the problem is that the internal states, they need to encode and remember both what's been going on recently and what's been going on a long time ago. And doing both of these things in practice turns out to be difficult. Even though in theory, if you make these hidden states high dimensional enough, this should work. But in practice, it's proven difficult. So one way to go about this is these LSTMs, so these long short-term memory networks. And they get a little more complicated. So usually a normal, simple RNN is just a feed, is internally just a linear, nonlinear cascade. So what happens is that you have the last state and the current input, they get concatenated. Then there's a linear operation on it, a matrix vector multiplication and 10H, and then you have the next state. These LSTMs, they're a bit more complicated internally. They introduce a bunch of internal gates, gating variables that act on different parts of the internal structure. The important thing for us at this point is that there's two internal variables now, one which is H, which is the hidden state as before, and produces a sequence for every time point. And then there's the second internal state, C, which is acting more like a fixed memory that runs as a backbone through time, and that gets modified at different points in time. And with this backbone, it's very easy to transfer information very long term from early states into the future, because if you don't add anything to it, it just stays the same. So remembering things is actually the default for such a LSTM cell. There's a bunch of different gates, as we will see in the paper and the equations for the convolutional LSTM in a second as well. These are all simple linear, nonlinear cascades, not even cascades, just linear, nonlinear functions that act on the different parts of H and C. Importantly, there's also different variants, and it gets more complicated if you add more parts to it. In fact, this one here is the basis for the equations that they use in the convolutional LSTM paper. So starting out from just LSTM equations, which are pretty much the same. I don't know if you can see this. This is getting a bit. So these are here the exact same equations for the different gates. What they do in order to make the LSTM convolutional is very simple. The interactions between the inputs X and the hidden states and the matrices, they simply, in the convolutional LSTM, they simply replace them with convolutions. So where before you had matrix vector products, you now have convolutions for the inputs and for the hidden states. And what this does is it effectively takes the hidden states, these ages that were vectors before, and turns them into tensors with all the spatial structure that comes with it. And the advantage is that the hidden states now have spatial structure. So they have, when the input image is 2D, then you have like longitude and latitude, then the hidden state has the same structure. There's a longitude and a latitude axis in there. I hear there's a question in chat. Linda, you had a question?
Sorry, I probably have a question.
Okay.
So, an input is one image or it's a stack of images?
So it can be both. So in principle, you can have only one image, but in both of the papers, in the convolutional LSTM one and in the MetNet, it's a whole stack of images. As we've seen here, you have actually 17 time varying images, 16 from the weather, 16 from the from different spectral bands of a satellite, and one being the radar. Actually, two. There's a downsample global one, and there's a center crop. So you have stacks of them. Another question? If not, I would give back to David.
Okay, thanks a lot, Marcel. I will take over the screen sharing once again. Right, so this is the initial phase of the network, which extracts features via the convolutional input segment and downsampling, then feeds these reduced dimension inputs one by one into this temporal encoder, which accumulates information as it moves through time. Specifically, it moves through 90 minutes and 15-minute increments. They actually have more data, but that's what they use. There's a limit to how much you can actually fit in there. And then they go into the next phase, which is self-attention. So this is an important and tricky concept. I'm going to try to explain it as simply as possible. So the basic motivation starts here, right? We want to make predictions in this little region, and we want them to depend on everything in this big region. Now, if you stack enough convolutional layers, then at some point, the outputs will depend on every pixel of the inputs. Likewise, you could have a recurrent network pass over all the inputs in sequence. But these both have their limitations. With ConvNets, if you stack them very, very deep, they become difficult to train, and they may not fit into memory. These are very large inputs. They may not fit into memory, they may take a very long time to train, and they may have a lot of parameters, which is not something that you want in this case because it leads to overfitting. Instead, what we'd like to have is a neural network layer, a unit of our neural network, which takes, in which the output on the next layer depends on every pixel of the input in the current layer. And one way of doing this is with self-attention. So I'm going to use Peter Bloem's blog post. I'm going to go over it very superficially, but I'm going to give some further links and further reading for anyone who wants to follow along. So we start with this idea. Let's imagine this really ultra simplified version, which wouldn't be useful, but is a good first step to explaining things, right? We have a list of inputs, x1, x2, x3, and we want a list of associated outputs, y1, y2, y3, and so on. And here our x's would be pixels of the input, and our y's would be pixels of the output. But it could be a lot of other things in different contexts as well. So imagine that every output y will be a weighted sum of all the inputs, where wij says how much input j should contribute to output y. And now how do we compute these weights? Well, in this ultra simplified version of self-attention, we simply compute them as dot products between the inputs. So if we want to compute output I, we're going to take input I, xi, take its dot product to basically measure how similar it is in a certain sense with all the other inputs. And then according to how similar these are, that other input will contribute to output I. So if we put this in visual form like this, right? We have our inputs here, x1, x2, x3, x4. Now we're going to compute the output y2. So that means we'll take input x2, we'll dot product it with x1 and make w2, 1. We'll dot product it with itself, make w2, 2. We'll dot product it with x3 and make w2, 3, and so on. So this gives us our w's. We put them through a softmax, which basically says put it through the exponential function to make it positive, and divide by the sum to get weights that sum to 1, and then use these, do a linear combination, and make y. Now, one thing to point out right away is that because we're using a weighted sum of all the inputs, each output, yi, will depend on all the inputs, x1, x2, x3, right? So we've managed to incorporate all the inputs into each output in a single step. Another thing to keep in mind is that while this sort of looks like it might be a linear operation, it's not. It is a weighted sum, but the weights themselves depend on the inputs. So if you plug these dot products in here, you can see that we're actually multiplying the inputs by each other. So this is a nonlinear operation, which gives it a certain expressivity. It can capture a lot of stuff. Now, one thing to point out as well is that there's no trainable parameters here in this ultra simplified version. There's nothing to learn. All it does is carries out a simple rule. Okay, so this is not really useful, but it is a first step. So then how do we go from here to an actual self-attention layer? Well, we add in these three matrices, which are actually parameters of the neural network that can be learned. And these are the key, query, and value matrices. So this is how it works. Instead of just taking the dot product of each x with every other x and then weighting the x's, we're going to use different versions for these three different roles, right? We have, so suppose we want to compute output 2 again, right? First, we'll take xi where I is 2, right? We'll multiply this by our query matrix. So we're basically extracting features in a linear operation that are relevant. So we're saying we want the output for an x with these features, and this matrix will do dimensionality reduction and just extract the relevant features. Then we need to compare it with all the other x's to see how similar they are. And there we use this key matrix. So again, it extracts features from each x. Compare these features to the features extracted with a query matrix from x2. And then we get our weights. And we put them through the softmax as before. So they sum to 1. Then we need to take that weighted sum. And when we take the weighted sum, we're going to take still different features extracted from each xi with a linear operation, right? So we have all our x's. We're going to extract some features to get the q's, some to get the k's, and some to get the v's. We then take our dot products as our q's times our k's, and then we do a weighted sum of the v's. So as before, we have nonlinear operations. As before, every input can affect every output. And again, our inputs here would be different pixels with all their different input channels, all the different spectral channels, the previous time points of the precipitation rate, as well as everything else. So that goes into the ConvNet, that goes out of the LSTM, and then this comes into our attention module. So we have a big vector going in for each pixel. And so having done all this, we're able then to get our new outputs for each pixel. But they depend on the values of every pixel in the input. And the trainable parameters, the parameters we learn as we try to match our data, try to get a good prediction on the training data, we adjust these W's. That's all we adjust here. Okay, so this is really nice. It solves this problem of not having to stack a whole lot of different layers on top of each other. It was introduced in this paper by Vaswani et al. 2017. It was originally used mainly for text. And why is it called attention, right? Well, whether you're trying to translate a sentence or whether you're trying to predict a precipitation pattern in the future, the reason it's called attention is because basically these three matrices, the query matrix, the key matrix, and the value matrix, they tell you for each of these operations, for each of these roles played by the x, saying which output we want, saying which other x's match, and which of the features we want to use from those other x's if they match. For each of these roles, we want to look at certain features. We want to pay attention to certain features of that x. And there's a whole very elaborate theory of different ways of doing this. We're not going to cover it, but I'm going to link in the YouTube description and on the website just this review by Lillian Wang of all these different ways of doing attention in images and text. And it's very intuitive. We want to ask essentially which features of these images should we pay attention to, which encapsulate the relevant information for predicting the precipitation at some point in the future, at some point in space. Where should we pay attention? And this is what the network learns, what part of the image to look at. Likewise, in the original papers where this architecture was developed, they were translating sentences. So for each word of the sentence, you want to know which other words of the sentence are relevant to translate the current word. And this all depends on the topics and the word order, and there's this whole theory on this, but this is how this stuff came to be. So this is good. And it allows us to get around this issue of having to stack up many convolutional layers in order to get an all-to-all dependence. But they do have a key limitation. And you can see that in the sum operation right here, or the equivalent one when we have the extra matrices. Basically, to compute one output, we have to sum over all the inputs. So if we have n outputs, then we have to do n sums with n elements, so we do n squared operations. So the memory cost and the computation cost are quadratic, in our case, in the number of pixels, which is a huge limitation. We can't have it grow with the square of the number of pixels when we're conditioning on these very, very large input patches. And even though we do a lot of dimensionality reduction in the initial data processing, right? If we look at the network architecture for MetNet, yeah, it gets reduced a lot, and I believe we're down by the time we get to the attention architecture, we've now, like we've seen in last week's paper as well, as you go through these layers, you increase the number of channels, but you decrease the spatial size of what's passing through the network. And by the time we get to the attention module, we're down to 64 by 64 from the original 1024 by 1024, but we have 384 channels instead of the initial 20 or so channels. Okay, but even 64 squared is just too much. So they use one more trick, which is a special reduced variant of the self-attention principle called axial attention, which is a very simple concept, right? Instead of letting all the outputs depending on all the inputs in the whole image, it will only depend on the inputs in the same row or in the same column. So first, we update every row based on the pixels in the same row. Then we update every column based on all the pixels in the same column. And having stacked up two of these operations, we now have every output depending on every input. So we still have to stack a little bit, but not nearly as much if we were, say, stacking up 3 by 3 or 5 by 5 convolutional filters. In the original attention paper, Vaswani et al., called Attention is All You Need, they have this very nice table which compares these different approaches, and really all of these ingredients are going into MetNet. You have the general self-attention approach, which involves a lot of complexity per layer. It involves number of pixels squared times channels. This is the memory and computation cost. But it has a path length of 1, meaning every output depends directly on every input. Then you can have a recurrent net, which requires you to do a lot of computations in sequence, and it still requires you to stack things a bit. You can have a convolutional net, right, where you have a filter such that the dependence of outputs on inputs grows with every layer, but you still have to stack a lot of layers. And then you have these various restricted forms of attention. We're not going to cover that here, but essentially you'll only need 2 operations instead of 1 if you use this axial approach, which is what the MetNet authors did. So if we review what they're doing, in their figure 2, they have their entire network. We start off with these big 1024 by 1024 images with 20 channels or so. We pass it through the initial stages of the network, which reduce dimensionality, which reduce spatial resolution while increasing the number of channels. We then pass these results through a temporal encoder, which incorporates this information every 15 minutes for 90 minutes total. We then pass it through the self-attention module, which then causes every output to depend on every input. And then finally, the output then consists of 512 different values, which are simply the 512 probabilities for a histogram. A histogram of what is a probability essentially of this categorical distribution describing the probability of every possible level of rainfall discretized into 512 values. So it has the ability to express the probability distribution at each pixel for the precipitation rate. And essentially, by reducing from letting all the inputs in this module all the outputs depend on all the inputs, by doing it row-wise or column-wise, we reduce the total computational cost from pixels squared to pixels times square root of pixels. So there's a big savings in memory and computation time, and what's still a very intense piece of computation. I'll just add they have put code online for, not for the whole MetNet, but for the axial transformers building on TensorFlow. So you can download this. It's from the same group that did MetNet, which is also the same group that did the axial self-attention at Google. And you can see it's a little more involved than the stuff we looked at the past couple of weeks, but still in less than 1,000 lines of code, they really have all the core elements. So you can download this and play around with it. Okay, so now we've gone over these different aspects of MetNet, how they build their architecture. I'm going to talk briefly about some of the results, make a few comments, and then I'll open it up to general discussion. So one interesting thing that they did is they want to predict at all different target times. Now, one thing they could have done is trained it for different target times, a prediction time of 1 hour in the future, 2 hours in the future, and so on. Instead, they actually made that an additional input to the network. So they provide it as an extra channel of the inputs. This is very similar to something that we covered in the first session, where we had those physics-informed neural networks, which took time as an input to the network again. I see there's a question in the chat. A couple questions. So Eduardo asked, the outputs are probability. How is the network trained? The observations are not probability. That is a very good question. They're not extremely detailed about it in the paper, but from what I can gather, they're maximizing the probability of the for the correct bin. So if you look at the actual data, the precipitation data from MRMS, they assign that to the correct one of those 512 bins, and they say we're trying to maximize the probability assigned to the correct bin by the network, or rather we want to maximize the log probability and then add that up for all the predictions. So that's equivalent to multiplying probability. So they're saying we want to maximize the probability for the correct bin of their 512 bin histogram. A second question is, why aren't they using the attention mechanism for the temporal encoder as for the NLP approach, the natural language processing approach? And the suggested answer is probably the computational cost, but LSTMs are also quite expensive. Yeah, these are good points. I think probably that is a major reason. LSTMs are also expensive, but they don't grow quadratically with the number of time points. They grow linearly with the number of time points. So maybe that's the reason. When they start to release code and maybe more detailed results, maybe we'll be able to answer that for ourselves if we get to that point. I'm just going to quickly check if there's any questions on YouTube chat. No, there doesn't seem to be. So I will carry on with a few more observations. Okay, so we have this adjustable lead time. We just covered that. Then they're able to express uncertainty, right? So you can see this here a little bit, and you can see this in a previous figure where they illustrate this, right? How if they have this binned histogram version of the probable outcomes in terms of millimeters per hour of rain at a given prediction location, and it can do a lot of interesting things, right? It can have a bimodal distribution here, so multiple peaks. It's not just a single mean and standard deviation. It could do things like all or nothing, which is to say, okay, it can say, oh, either there's a big storm or there's nothing and nothing in between. This is a kind of uncertainty that's capable of expressing. What it can't do is express correlations between nearby pixels, right? So if we look at these predictions, and this sort of explains, they're fairly blurry. So here's our ground truth, and here's, the numerical weather prediction model, the physics-based model they compared to and really claimed to beat. It actually looks very similar by visual inspection to the ground truth precipitation rate, whereas theirs looks a lot blurrier, although it does capture some features that are missed by the numerical weather prediction model. But, well, it's blurry in a sense because what they're reporting here is basically a thresholded version where they say that, they're reporting the probability of precipitation above some threshold, in this case 1 millimeter per hour, which really is just breaking that whole distribution, which may have multiple peaks down to a single number. For one, we don't know if the network actually ever did express multiple peaks in that distribution. Does it have bimodality? And we also don't know, so it may have done that, it may have not. The other thing is, it can't express, as I mentioned, correlations between neighboring pixels. So if you think of wanting to express possible outcomes, if you want to express uncertainty, you might like to make statements like or statements or and statements. For example, I might say, well, either there's a storm here and it'll cover a given region, or there's not. But the MetNet actually treats individual pixels independently. It expresses uncertainty about individual pixels outcomes in the future, how much rain we'll get there, but it doesn't express that, okay, if there's rain here, then there's likely to be rain right nearby. On the other hand, if there's rain here, there's not going to be rain somewhere further away because there's only one storm and it's got to be in one place or the other. So it only expresses uncertainty one pixel at a time. And it gives us these blurry outputs. We can't get realistic samples out of this method. Okay, now another question is, how do they evaluate performance? They use this F1 method, right? So F1, and we'll link, I think, to the Wikipedia article. F1 is defined as precision times recall over precision plus recall times 2. So precision is basically saying, if MetNet thinks that a given pixel has a precipitation over 1 millimeter per hour, what is the probability that there really was? So it'll be 1 if we have perfect precision, and it'll be a lot less if we don't. So it's basically the rate of true positives over true positives plus false negatives. And then recall is saying, if there really was rainfall over 1 millimeter per hour at some location, what's the probability that we detected it? So when these are both equal to 1, we have perfect performance, and we get 2 times 1 over 2, and we get an F1 of 1. That's the best possible score. And as we have worse performance, it heads down towards 0. And so they use this measure, and they compare their forecasts to their numerical weather predictions provided by NOAA, I believe. This HRR system, which basically runs, initializes using an ensemble method, I believe, and it runs the deterministic physics-based weather prediction into the future. And then they ask, how do they do compared to these predictors? I think they have this on their blog post as well. Yeah, right. So you can see the numerical weather prediction based on physics in green, MetNet in blue. So for short time delays, they're doing significantly better. And then as you go further in time, at about 8 hours, there's a crossover point. And there the neural network really fails to do as well, and it'll keep degrading because it doesn't have any concept of physics. So this is how they measure accuracy, and this is how they claim to be better than the physics-based model. And I'll be really curious when we open this up in a couple minutes to questions what people think of this, who have maybe more of a grounding in climate science and weather prediction. So they also do these ablation experiments, which is to say they limit some parts of the inputs or structure of the network. They do several of these. They reduce the input size from 1,024 to 512 kilometers. And this reduces, as you'd expect, the performance. And I know it sort of fits their argument that the more in the future you want to predict, the larger of an input patch they need. And in fact, they don't see much of a degradation until they go 150 minutes into the future. So for short time delays, it doesn't matter if you look at 512 kilometers input region or 1,024. But beyond that, it starts to degrade. The numbers don't exactly add up. 150 minutes, versus 512 kilometers. It's a bit funny in that it doesn't really match their number of 60 kilometers per hour speeds, but it doesn't really matter. So they find that, as you'd expect, the longer you want to predict in the future, the more of an input patch you need. The other thing they do is they look not as far back into the past. They only look 30 minutes back instead of 90. It doesn't make a huge difference. And then finally, they ignore the current precipitation and only look at the satellite imaging. So they ignore the ground-based radar completely. And they find that this makes things worse for short time delays, but when you go far enough into the future, the current precipitation state doesn't tell you that much, and you really just want to look at satellite data to do longer range predictions. So finally, before I turn it over to questions and comments, I will quickly, so Stefan Rasp called my attention to this Twitter exchange he had with the authors, just asking some questions, making some comments, and I thought it'd be great to call everyone's attention to it. So the first thing he points out, which I think is really interesting, they did an insane amount of computation to train this network. So 256 parallel TPUs, tensor processing units. These are basically printed integrated circuits that you can buy or rent from Google. So, I mean, they're a little bit more powerful than a top-of-the-line GPU, but they have 256 of them. So this is really a lot of computation they did, and it's quite some doing. This is seriously industrial scale. Something to keep in mind. It's not so clear that this is accessible to most academics. Another issue I think that he calls attention to, which I think is really worth mentioning, so he compares, if we look at the WeatherNet and the ground truth and the physical model, you know, it's a little bit of an unfair comparison because even if you have the right features, they may be slightly misaligned pixel by pixel. And is it better to have something which is slightly off by a few pixels but has the right features and the right sort of characteristics and looks the same as a ground truth, or whether you rather have these blurry things which maybe match better an F1 score but don't look anything like weather patterns? And so it's a question of whether this is really a fair comparison using the F1 score, where if the physical prediction gives the right answer but is off by even 1 pixel, it's treated the same as if it were, you know, 100 kilometers or 1,000 kilometers in the wrong place. So in principle, if you just applied some kind of blurring filter to the physical model, you might actually have prediction accuracy which is much closer to MetNet or even better. And it would be very easy to estimate what these blurring parameters might be, but they haven't done that. In practice, these physical models used for weather prediction wouldn't just output a single deterministic prediction, but actually a whole ensemble of these predictions. So there's uncertainty there as well. But the authors responded to him on Twitter, and they also correctly pointed out that, unfortunately, HRR didn't provide the ensemble. So there's really nothing that they could do about it. The other point that he raises, I think, which wasn't really addressed, is they claim in the paper that they're able not only to capture advection, that is, you know, the way clouds move around, and the way that affects rainfall over time, but also the formation of new convection patterns and new areas of rainfall. And Stefan, I think mostly correctly, says, well, in fact, there isn't really a lot of new rainfall appearing in MetNet's prediction, except in regions which already had convection at time zero. If there's one spot where maybe it's happening, it's in the southwest corner of Lake Erie, not in fact too far from my hometown in Indiana, but you see this kind of blips on and off, whether that's really new or whether it's a function of all the stuff that was happening before in the data. As we look 90 minutes back in time, it's a bit of a tough call. But whether we really see new patterns forming, like in the physical model and the ground truth, is sort of debatable. And there's one final point I want to just call attention to, which is an interesting point. I think I mostly agree with it, but it's sort of controversial, and I think it's worth mentioning. So toward the end of their section 5, the authors of MetNet make this statement. for numerical weather prediction, that is physical models, is the performance of numerical weather prediction is inherently tied to the spatial resolution of the model, since increased resolution allows more physical phenomenon to be directly resolved. That is to say, for one thing, you have all these expertly, tuned by hand, by humans, model parameters. So you have parameter tuning in the numerical physics-based weather prediction model, and that was tuned for a specific spatial resolution. So if you go to to coarser resolutions, you may lose that. There's also a lot of processes in the physics, all these different spatial scales where the physics is actually happening, and if you don't have a fine enough grid, you won't resolve them, and your model won't give the right answer. On the other hand, all the implicit subgrid, subspatial scale dynamics that are happening, you can kind of just integrate them out when you train on coarsified data, right? You don't need the laws of physics to hold in your neural network. There's no physical model at all in MetNet. It's just learning from data. And that means it doesn't really care if you resolve these fine processes which you need to really explain how condensation happens, how convection happens, how rainfall happens, in a physically plausible way. If you don't have to be physically plausible, all you can say, okay, well, at this resolution, I see this. So in the past, on average, when I saw this next thing happened. So they're not, as I say, MetNet performance is not directly tied to the resolution, since the network can learn to represent any sub-resolution structure in the hidden layers. I think the statement is mostly true, but I'm not totally convinced that that you can really, of course, when you go to coarser resolutions, you're still going to lose information, and as a result, your performance will get worse. So, okay, that's basically all I have on the paper itself. I have questions that I wasn't able to answer that I'm curious about, but before that, I just want to open up the discussion. Anyone who has a question, you can write in the chat or just raise your hand on Zoom. Yes, Eduardo.
Yeah, hello. Actually, I had more of a comment rather than a question. Well, first, thank you very much for the very nice explanation of the paper. Can you hear me?
Yeah, I hear you fine.
Yeah, okay. So my comment is that actually, when you compare the skill of the neural network compared to the physical-based model, as a function of prediction time, of lead time, and you find that actually after 8 hours, both are roughly the same. I was wondering if actually what the neural network essentially is doing is learning the flow. So from the satellite bands, actually the information is basically the radiation balance or the clouds. So it's following the flow of the clouds, and basically it's interpolating this flow into the next hours. And when we go for predictions for lead times that are beyond, let's say, a reasonable extrapolation, when physics dig in more strongly, then the neural network, or the skill of the neural network, then becomes lower than the physical model. Of course, the neural network is very complicated, as you have explained, has a lot of pre-processing and post-processing. But my feeling was that actually if you could summarize the working of this neural network, is just almost a visual interpolation and extrapolation of the flow. I don't know if that's a fair, let's say, a fair comment.
So it's a good question. I don't have a perfect answer for you. I can give you some information. So one of the things they do, you can see on this graph here, is in addition to comparing to the numerical weather prediction model, the physics model in green, they also compared to an optical flow model in red, where this model only tries to track movement within the image over time. It doesn't have anything like new new convection happening. It's only tracking parts of the image as parts of a moving image. And these are the kind of the algorithms you use in self-driving cars to track objects on roads. So you can see it's much worse than MetNet. And actually, even at much shorter lead times, it gets worse than the physical predictions. But is it a fair comparison? I mean, they didn't use 256 tensor cores and a huge computational budget and all the very latest cutting-edge neural architectures in this optical flow method. So it's difficult to say if it's a fair comparison. It's also difficult. So what would be nice is if we could use all these computational tools, but still restricted to only use flow. So we don't really have a way of doing that. So we don't have a complete answer. At least we can say a tailor-made flow detection method doesn't work as well. And then it goes back to exactly this thing that Stefan was saying on Twitter. Are there really new spots forming? And even if you can find that in individual examples, how much does that contribute to the overall performance? And we really don't know that for sure. Corinna, you had a question as well. Got your hand up. I think there's a question in chat, so let me read it out because you're still muted. Are input data precipitation data? Would it not be more promising to use other information such as atmospheric stratification and dynamics? Yes, I mean that's a very good question. We have a lot more information in our numerical weather prediction models, and it would be great to feed that into the networks. We're not doing that. Partly it may be memory and computation constraints, but it may just be that it hasn't been tried yet. What's being fed in are precipitation data as well as these 16 channels of hyperspectral satellite-based imaging, and I believe we have a diagram here, yeah, as well as a few other things. We have an elevation map which goes in, we have latitude and longitude maps, we have month, day, and hour maps, just the month, day, and hour of the prediction will go in as a single number to all points in space. So this essentially allows us to implicitly condition on, the season, when the sun rises and sets, everything like that. So there's a lot of that information going in, but there's a ton of information that could be used when we consider what the numerical weather prediction method, the physics-based method, actually has access to. So we haven't really combined them. What we have is a purely data-driven approach here, which doesn't use any physics. Andre, you've got a question.
Yeah, do you hear me?
Yeah, I hear you fine.
Yeah, so I just maybe missed a little. So what kind of physical model do the authors use for comparing with the neural network?
Yes, they use this HRRR, which is also from NOAA. This is the high resolution rapid refresh. So it uses a 6-hour delay, just because it takes them 6 hours to process it. They spin it up. I believe this is an ensemble Kalman filter, but I don't know that. There are references given in the main paper. So they publish the precipitation rate data as well as other inputs to this numerical weather prediction system.
Yeah, and I also want to make one comment on Karina's question. So sometimes, when you fed your neural network, it's very unpredictable how it will behave. For instance, I do my stuff with chemicals, and chemicals they really depend on the temperature. So, and what I get, so that if I have wind and some kind of water in the atmosphere, so humidity in the atmosphere, then this is enough to get a good forecast with neural network. If I add temperature to that, so my quality of forecast gets worse. However, if I throw away these things and take, say, pressure, temperature, and concentration, so then these things explain everything almost. So sometimes, there just combination of variables. They are not matching to each other. This might be why they used this set of variables as inputs.
Yeah, thanks. It's a very good point. And if you actually really want to predict what the weather is going to be in the future at some point, there's a lot of variables. And using that with temperature in chemical models. Karina is mentioning all these physical variables in a numerical weather prediction model, which are not going in to this prediction. One possible argument that the MetNet authors might make in their defense, I don't want to speak for them, but so again, we're conditioning on these large patches, right? So we're conditioning on really very large regions, and we have all this spatial structure of these 16 image channels and the weather prediction at some 6 points in the time points in the past and the present, right? So we have a ton of information. So if you have some variable which is not resolved, say, wind speed, it may be possible to implicitly recover any information in that variable from this huge wealth of information we're pushing into the algorithm. So it may be that any information which you'd want to get from something not resolved, like wind speed, the exact nature of the cloud cover, anything that the algorithm doesn't have access to, everything MetNet is not given, it may actually implicitly reconstruct that in its internal representations. It may be able to guess the missing information from the pattern of precipitation in the past and the satellite images. It might be possible, it might not. It really just depends. Eduardo, you got your hand up again. Do you want to ask your question?
Well, I actually wrote my question in the chat. It was again, about the self-attention algorithm that you explained before. So if I understood it properly, it's a method to identify the main features in the input that actually are most strongly connected to the output, right?
Correct.
Yeah. So that is something like a sort of causality analysis in neural networks. So just to find out what are actually the main drivers of the output.
Yeah, I think that's mostly accurate. So you'll find so the people who work on this stuff, it's a very different branch of mathematics and machine learning than causality analysis, but some of that language does creep in. So let's go back to the Axial Attention paper where we do one row or column at a time. What they do is they use these masks. So as they construct this row, they want information to flow from left to right, in that as they generate the pixels of the output, they may condition not only, you can of course condition only on all the inputs to all the outputs in one step and that's it. But what you can also do is create the first output, and then when you create the second output, you condition on all the inputs as well as the first output you just created. And this is an auto-regressive model with a causal structure. And in the self-attention papers, they will even use the word causal to refer to the specific structure of the neural architecture. So it can be thought of as a kind of causality. It's not causality in the sense of actual physical causes or of Granger causality or other kinds of causal inference that might be done in earth science. But it's a similar concept in that you have things depending on each other in a certain order, a certain graph of connections. Yeah. So one more question from group chat, and yeah, if you want to ask your question, just raise your hand in Zoom and I'll call on you. You can also just post in the chat and then I'll read it. It's important to read it, I think, because YouTube viewers can't see it. So one more question from Tobias Weiger. A comment, rather. I'm wondering whether the axial variety of the self-attention algorithm favors the exemplary U.S. weather pattern, as the axes are NE and S and S, like northeast and southwest, north, south, east, west. I'm guessing. I'm not sure. I'm a little. Yeah, some type of. Anyway, they align to the compass pretty well. Is not a sophisticated radial approach like we had talked about last week, where we discussed spherical convolutions. Could also have an influence. Yeah, and that's certainly true. There's a number of questions one could raise. Yeah. The whole point of this is not to consider all the inputs at once, but to go on different dimensions, so that when you go along rows and then you go along columns, and after a few of these operations, a small number, all the outputs depend on all the inputs. But of course, you could do another pattern. Instead of rows and columns, you could do some radial representation. You could go along radial lines. You could then go around circles around a center point. This is also possible. It's also worth asking, they're covering a pretty big region, 1,000 kilometers, so the Earth isn't exactly flat across the continental US. And yet, the initial phases of their network are convolutions. They don't seem to deal with any of these curvature issues that we discussed last week. So it's possible that if one replaced these with some kind of other convolutions that took into account the curvature of the Earth, one might be able to improve the performance somewhat, especially perhaps for weather patterns which are traveling north to south or south to north. Okay, so I don't see any more questions just now. Eduardo, you have your hand up again. Do you still have a question?
No, sorry.
Okay,
it was a mistake.
I want to go quickly over some questions of mine that I couldn't. So the number one thing I like is, as someone who comes more from the machine learning side of things, I'm very curious for some kind of scientific / aesthetic evaluation from people who are more on the weather prediction and climate side of things and earth science. How useful is this? Is this a promising approach? Is this something that is worth pursuing? It's a very general question, maybe too general to get an answer. While people think about that, let me ask a more specific one, which is, so they argue for these sizes based on this speed of movement of, say, 60 kilometers an hour or about 27 meters per second. Is this realistic? And even if it is realistic for the rate of movement of clouds, is this really the relevant speed limit? Or are there other forms, other physical processes, like maybe wind speed in the upper atmosphere, that might move much faster and carry information from point to point much faster than the movement of clouds? Is this a reasonable limit, or does one have to maybe consider even broader contexts? At least their ablation experiment, where they cut the context size in half, and at least for the first 150 minutes, it didn't seem to matter. Yeah, Tobias.
Yeah, I think so. They showed in the ablation study that with their experiment with a smaller region, they have around about a wind speed of 208 kilometers per hour, and I think this is roughly, or this is I would say it's a first guess for the wind speed in the upper troposphere. And so I think that especially convective clouds can travel with this wind speed. And I have to admit that I'm not really convinced by this paper, because I also worked on radar data, and I think it's a quite unfair comparison between the numerical weather prediction model and the MetNet model, as Stefan already raised in Twitter, that they only compare the F1 score to, with the F1 score, their model with the numerical weather prediction model, and I think it might be not the right metric to compare these two models. And so I'm not really convinced by this paper, I have to say. And
well, that's good. That's really interesting. That's good feedback to have. I mean, what I would find a little more convincing, and I mean, look, they haven't submitted it to a peer-reviewed publication yet, so they may still be working on it, doing other things, and hopefully they'll release code that we can test as well. But what I would find a little more convincing, without too much more work, is if, in the neural network case, in MetNet, you're training 225 million parameters, right? Insane amount of computation, probably the energy budget of a small city for a year. But what I would be maybe a little more convinced on is if they would just train one parameter for the physical model, which is the size of Gaussian blur, which gives you the best F1 score. So if you would just, how much should we blur the outputs of the physical model in order to get the best F1 score, and then compare that to MetNet? It would be pretty easy to do, I think. Andre, you have a question?
Yeah, I just had a comment to your question. You asked about the wind speed. So as I know, so the wind speed at 10 meters, the average is about 7 meters per second. So it's I estimate it's something like 28 kilometers per hour. So so the hurricane has the hurricane starts from 20 meters per second, so which is 72 kilometers per hour. So they say have strong wind, but yeah, not hurricane. That was my comment.
Yeah. Okay. Yeah. And it may well be whether this doesn't work in these extreme weather situations. So one point I forgot to mention, which is interesting too, is that an advantage they potentially have over the HRRR, the numerical weather prediction based on physics, is that takes a long time to run. And while this takes quite a long time to train, they didn't say how long, but I'm sure it took a while. Once it's been trained, you can get a prediction in seconds, independent of the prediction time, whether it's for 10 minutes in the future or whether it's 8 hours in the future. And I think they claim somewhat reasonably that the supercomputer used by NOAA might take an hour to make an 8-hour prediction. So they can actually, their prediction is going to be ready 1 hour earlier, which is quite cool here. I want to make, well, first I'll make a technical question. I want to give a technical question. I didn't quite understand something when I was reading about the architecture of their neural network. So after the LSTM, they, another comment from Tobias Weigel, yes, it would be very cool to get our hands on the trained network and then just to try it out in different regions and different weather conditions. And really we have these F1s and we have a few individual examples, but it would be great to have more of an exploration of what kind of mistakes does it make, where does it do much better than the physical model, where does it do worse, in what conditions do they both fail or both succeed. We just have a very superficial understanding of what the strengths and weaknesses are, but it'd be good to know more. So one other question I have here is, well, how have they, when they built this thing, let me find the place in the text where they describe this, because I got a little confused when they describe the architecture. So they have the downsampler, the convolutional steps, then they have the recurrent network, the LSTM, and then out of that comes 64 by 64 pixel image with 384 channels. So like this pattern we keep seeing, they reduce resolution quite a bit while increasing the number of channels. But then when they do the self-attention block, you're operating on one row, so that should be 64 pixels with 384 channels, and somehow this comes to 2048 channels total, which is a power of 2, which 384 is not. So some other action is happening in between the output of the LSTM and the input of the self-attention blocks. And it's not clear to me what's happening. Something is happening. I hope they'll describe this in the next version of the paper on arXiv or the peer-reviewed journal. I hope they provide the code so we can actually see what they've done, because there's a number of points where this is a little unclear. It would be very interesting to know these details. And finally, I want to just give one, personal perspective on some of this on a much higher level than any of the scientific topics. And this is just my own personal view. It doesn't represent, anything or anyone else, which is that, what they've done is quite impressive. But I think it's a little unfortunate that is happening with the resources of this huge company that has all this amazing hardware and is able to hire a lot of great scientists and programmers out of academia or other institutions like NOAA, where they might be doing public domain research. Then these guys are working on an important problem, whether as that relates to climate and weather extremes with a lot of human impacts. But the code, whether it's something like this for weather prediction, or whether it's something like Google DeepMind learning to play Go or chess, it's typically not released in the public domain, even if some bits of it are, like this axial self-attention blocks were. And it's a bit of a shame that in the end, while these scientists are working on predicting important variables with big human impacts, it's quite likely that code will be held onto as the intellectual property of Google and be used to kind of optimize, web-based advertising. It's also unclear. I think maybe someone with more experience with the computing architecture could answer this. It's a little unclear to me how much of an ask it would be to get a hold of 256 TPUs, these printed circuits that you can rent or buy from Google. How much would it cost to train this network in dollars and in kilowatt hours? And that kind of puts things into perspective a little bit. They're comparing this to other methods, whether it's a physical model, the optical flow, or other neural network approaches they cite, like UNet approaches, which certainly did not have the same computational resources. So it's sometimes difficult to disentangle what was the special nature of the hardware they had access to and the funds they had access to versus what is actually a better algorithm. But despite that, I think this is a very interesting paper for me. They did a lot of interesting things. They put together a lot of components, and they're able to get something which really hasn't been done before, which is at least on some measure, even if it's not the fairest measure, to beat physics-based prediction at short lead times. So that's basically all I have to say. Does anyone else want to add anything on the paper, on any other topic before we close? Yeah, Tobias.
Yeah, I checked the cloud TPU pricing at the Google page, and for an older version of the TPU, a TPU with 256 cores costs $192 per hour. So it is roughly, if one would 1 year commitment do, it would be 88,000 euros per month.
88,000 per 1 year.
No, per month. So
per month, 88,000 per month. That's not an insignificant amount of money.
No, it isn't.
It's not totally out of reach if one could justify it. But what's amazing for these guys working at these places like Google Brain, Google Research, Facebook AI, DeepMind, OpenAI, is not only do they have access to buy that time, they can just play with the system until it works, because as anyone who's worked with this stuff knows, it's never the first time you run it that you get nice results. So there's a lot of trial and error. So it's just quite a significant cost. But okay, not totally out of reach. So maybe if you already had everything set up perfectly, you could get it to work in a week. And so maybe it's only 22,000 euros. Yeah. Well, thanks for that insight. Any other questions, comments? We managed to reduce our running time to an hour and a half. I hope we'll eventually get this down to an hour as requested. We will see about that. Thanks a lot to everyone who participated. I think we will go ahead with a once every 2 weeks plan. I think this will give people more time to read the papers and familiarize themselves with the topics. I think we'll go ahead like that. And then I think in the future, if we have a lot of people wanting to present, we may increase the frequency. But for now, I think it'll be once every 2 weeks. Thanks to everyone for participating, and we will see you in 2 weeks. Stay safe and stay healthy.
Thank you. Goodbye.
Goodbye.
Very
Thank you.
interesting. Bye-bye.
Bye.
Thank you.
Bye.